Okay, we are going to just cover some counting rules here in this video, and hopefully we won't have to do this in class, therefore. So let's look at this. Suppose that an experiment involves a large number, n, of simple events. So we've talked about experiments like rolling a die, and we've talked about the outcomes, or the sample space, the set of outcomes. And they're saying basically that there's the sample space is large, because that means the simple events there are many simple events. And you know that all the simple events are equally likely. So remember that we talked about when the simple events are equally likely, we can use a very simple formula. Now they're using this notation here. Here you can see it. This is n sub a, and I, if you recall, for an event a, I used n of a. So I use this notation n of a, and they're using n sub a. So it's the same thing, just a different notation. So it means the number of elements in a. And so we talked about this formula where we have n of a. We have the probability of a is equal to n of a, as I wrote it, or they're writing it n sub a, over the total number of elements in the sample space. Now, we wrote this, n of s, on the bottom. So they're writing n. So n is equal to the number of elements in the sample space. Okay? So suppose we have this situation. In this section, we present three simple rules that can be used to count either n, the number of simple events in the sample space, or the number of elements in A. Or the number of elements in A. So the number of simple events in the event A. So we're going to have some rules that are going to help us to figure out in maybe slightly complicated cases, what is this and what is this. Okay, so let's see what that looks like. So first of all, we talk about the MN rule. So suppose that let's look at an example before we read that. So here's a candy dish, contains 1 yellow and 2 red candies. 2 candies are selected one at a time from the dish, and their colors are recorded. How many simple events are there in the sample space? So let's just see the answer to this before we go back and read the other. So the first candy can be chosen in 3 ways, right? So there is a red R1, there's R2, and yellow. So there are 3 different ways that we can choose the first candy. We can get any one of those 3 candies. So that's what they say. The first candy can be chosen in m equals 3 ways. Since one candy is now gone, the second candy can be chosen in n equals 2 ways. So how many how many simple events are there? So we did it like this. Whoops, I don't know what that is. We did it like this, that, and that. We said you could get yellow, you could get R1, and you can get R2. And then, if you got yellow, then you only have 2 possibilities, R1 and R2. If you got R1, you only have 2 possibilities, yellow and R2. And if you got this, you have 2 possibilities. Okay, so we said there's 3 sets of 2, or 3 times 2, and that's an example of this, what they call the, the MN rule. So let's read it now. Suppose that an experiment is performed in 2 stages. So that's what that example was. We took 1 ball, and then we took 1 candy, and then another candy. If there are m possible outcomes for the first stage, so there's 3 possibilities when we draw the first candy, and for each of these outcomes, there are n possible outcomes for the second stage. So there were 2 possible outcomes for the second stage. Then there were 3 times 2, or 6 possible outcomes for the experiment. So that's called the MN rule. Okay, so we have this example of it here. And then if there are, here, so we can extend the MN rule if we have more than just 2 stages. So if an experiment is performed in K stages, not just 2 stages, with N1 possibilities for the outcomes of the first stage, and 2 possibilities for the outcomes of the second stage, and so on, all the way out to the last stage is NK possibilities, then the number of possible outcomes for the experiment is not just N1 times N2, but it's N1 times N2 times N3 all the way out to NK. So here's an example of that. So a truck driver can take 3 routes from city A to B, 4 routes from city B to C, and 3 from city C to D. When traveling from A to D, if the driver must drive from A to B, and then from B to C, and then from C to D, how many possible A to D routes are available? So it's so going from A to B, so this is like going from A to B. So there are, what did they say? They can take 3 routes from A to B, so there's these 3 here, and then 4 routes from B to C, so I guess we'd have to say from B to C, there's 4, so there's 4 ways to go from B to C if you go this way, and there's 4 ways if you went to A this way, and so on. I'm sorry, if you went from B that way, there's 4. So we have that. So there's 3 sets of 4, and then 3 from C to D. So that's another 3 for each one of these. So it's going to be 3 times 4 times 3. So that's an example of what they called the extended MN rule. So this would be 3 times 4 times 3, right? Okay. So this helps us to count how many routes are possible, or how many outcomes are possible. So there's 3 times 4 times 3, which is, 36 different possible outcomes. Okay, 36 different possible outcomes. Okay, the next one, a second useful counting. So the first useful counting rule was the MN rule, or the extended MN rule. A second useful counting rule that follows from the MN rule and involves orderings or permutations. Okay, so what does that mean? For example, suppose you have 3 books, A, B, and C, but you have only room for 2 of these on your bookshelf. In how many ways can you select and arrange the 2 books? There are 3 choices for the 2 books: A, B, A, C, and B, C. So in other words, you could choose books A and B. That would mean leaving out C, so you wouldn't have chosen C. Or you could just choose A and C. That would mean leaving out B. You wouldn't choose B. Or you could choose these 2. Okay? But each of the pairs, so A and B, for example, is a pair, can be arranged in 2 ways on the shelf. So you could put A first and then B on the shelf, or you could put B first and then A on the shelf. So the combination, we call these the combinations of the 2. We can do AB, AC, and BC, but we can also reorder AB. So instead of we're still choosing A and B, but we're instead of putting A to the left of B, we can put B to the left of A. So we get 3 of these, but then each of these can be ordered either this way or this way or that way, this way or that way. So we have 6 possible orderings of the 3 books when we take just 2 of them. So let's see what they say. So that's called, by the way, that's called 6 different permutations. All right, let's keep going. So the MN rule implies that there are 6 ways, because the first book can be chosen in 3 ways and the second in 2 ways. So the result is MN equals 6. Okay, another question. In how many ways can you arrange all 3 books on your bookshelf? So these are called permutations again, because permutations are when the order that you write them in makes a difference. So you can write ABC, but you can also switch the order. So you could write it this way. That's the same books, but it's not in the same order. So then we call them permutations when you say that the order that you write them in or that you place them in is important. Okay, in how many ways can you arrange all 3 books on your bookshelf? There are 6 permutations. So you can do ABC, ACB, BAC, BCA, CAB, and CBA. And a way to count that would be to say that the first book can be chosen in 3 ways. So we can put in the first place, we can put either A or B or C. So there are 3 choices for the first place. Once we've chosen something for the first place, there are 2 ways for the second place. So once you've chosen A here, you can either put a B here or you can put a C here. That's the only possibilities for the second. And then once you've chosen something for the first place and something for the second place, there's only 1 choice for the third place. So we have 3. So by the extended MN rule, we have 3 times 2 times 1, which is 6 ways to permute them or arrange them. So this is a kind of notation for that last question, and this is one way to get the answer to that last question. So we already know that the answer to that last question was 6. There were 6 ways. Okay, so whatever this turns out to be, it better be 6 for that last question. This calculation should end up being 6 for that last question. So what is this notation? Well, we said in the last, let's take the question before. So that was when we took just 2 books. So how would we write that using this notation? We're choosing from the 3 books, we're choosing 2. So the way that is denoted in this notation is that and that. So you're choosing from an original set of 3, you're choosing 2, and we are concerned with the order that we write them in. So we use the permutation, which is P. Now it turns out that this formula will give us the correct answer. So I think in the previous, what was it with, I think in both cases actually, when you start with 3 and you choose 2, we also got 6 actually. So, and by the way, the last example that we did was when you start with 3 and you choose all 3. And that was also turned out to be 6. So both of the last 2 questions, the answer was 6, but the questions were 3 choose 2 and 3 choose 3. Okay? Now, this is supposed to give us the answer. So first of all, we need to know what this means, but I think we know what that means. So n factorial is n times n minus 1 times n minus 2 all the way down to 1. And you should remember that 0 factorial is equal or defined to be equal to. This means defined to be equal to. not just equal to, but it's by definition equal to 1. Okay, so let's keep going. So, well, the formula that we just saw was here. So it was n factorial over n minus r factorial. Now, in the last example, n was equal to 3 and r was equal to 3. So if we put those in here, what do we get? We get 3 factorial on the top, and on the bottom, we get 3 minus 3 factorial, which is 0 factorial, but that's defined to be 1. So what do we get? We get 3 factorial on the top, but what is 3 factorial? 3 factorial is 3 times 2 times 1, so it seems to work. We did get 6. So this formula seems to work at least in this one case. And how about in the other case? How about in this case? Does it also work? Because this we also expect to be 6. So what happens then? So that we have 3 here, so that's 3 factorial on the top. And on the bottom, we have 3 minus 2. N is the top, r is the bottom. 3 is the top, 2 is the bottom. 3 minus 2 is 1 factorial, but 1 factorial is 1. So we get 3 factorial on the top and 1 factorial on the bottom, or 1. So we still get 6. So this seems to work at least in both of the cases that we've done, or problems that we've done so far. So let's see. They just are going to show now that this, which is what we said, this is the, remember this is P, N, R. That's what we said the answer is going to be. They just want to show that this, if you write it out, turns out to just be equal to this. So what does that mean? So write this top part out, you get all that. But what they do is, normally we'd say n, n minus 1, n minus 2, and then we just write 3, 2, 1. But they're putting in 2 extra pieces in filling in here. Like, these are there, but we usually don't write them. So they say there's an n minus r plus 1 term. That's true because this is less than n. Okay? You can, if you don't believe that, just check it. Make sure you agree with that. And this is also less than n. So you can put these in there. And this one, what comes after this term? This is n minus r plus 1. So the next term is without the plus 1. So it's just n minus r. So this is all correct. We can write it this way. Okay, so we have the top can be written like this, and the bottom is n minus r factorial. But here is actually n minus r factorial also. This is n minus r factorial, right? So this is n minus r factorial. So this n minus r factorial, which is here, is the same as here, so they cancel. So all you're left with is from here to here, which is what they wrote below here. Okay, so we've shown that this can also be written like this. Okay, a special case, arranging n items. The number of ways to arrange an entire set of n distinct items is p n n. Well, we did that already. We already asked if we had 3 books and we chose all 3 of them, how many ways could we arrange them? And we said it was equal to 6. We figured it out. And they say that the answer should be n factorial, but here's n, so n is equal to 3. So it should be 3 factorial. Well, it is 3 factorial. This is 3 factorial. So, but let's show that this is basically true all the time. How do we show that? I guess we have to go back to here and say that if we have n here, and r is also equal to n, that's what we're saying, r is also equal to n, then what do we get? We get, let's just look at this part, we get r is equal to n, then we get n minus n here, so that's 0 factorial, that's 1, so what do we get? We get n factorial. Okay, so that's just a consequence of this fact. So this is the big fact, and then specifically when r is equal to n, that is when we have p and n, that is when we start with n items and choose all of them, all n of them, then the answer becomes n factorial. So that's kind of useful to remember that. Okay, so that's what they wrote here. Okay, so let's see if we can use all of these formulas. So 3 lottery tickets are drawn from a total of 50. So there's 50 lottery tickets, and we're going to take 3 from the 50. So 50 different tickets. We can imagine they're labeled 1, 2, 3, 4, 5, 6, up to 50, and we're going to choose 3 of them. If the tickets will be distributed to each of 3 employees in the order in which they are drawn, the order will be important. Because, for example, suppose there's only one winner, so and suppose that one of the 3 is the winning lottery ticket, then whoever gets it is going to be happy, and the other people are going to be unhappy. So the order is important. Okay, how many simple events are associated with the experiment? So what is the sample space? I would say, what is the sample space for this? So there are 3, here's the sample space. So there are 3 employees. So here's employee 1, employee 2, employee 3, and so it's possible that employee 1 will get ticket number 50, and employee 2 will get ticket number 22, and employee 3 will get ticket number 28. Okay, that's possible. Now, is that different than if we put the 20, we move these 2? Yeah, that's different, because suppose 22 is the winning ticket, then in this case, the second employee gets the winning ticket. In this case, in the other case, this employee gets the winning. So it's different. So what we're saying is that for this question, the order that we write the sample space in is important, or the order that we write the elements of the sample space in is important or relevant. So then really what we're saying, so the question is how many elements are going to be in the sample space, because this is just one element in the sample space. This would be one possible case, one thing that could happen when we distribute the 3 tickets. Another, as we just said, could be 22 first, 50 next, and 28. So that's, whoops, I don't know why it does that. That's another element in the sample space. Now you can see there's going to be many, 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 many elements in the sample space. So our question is, how many elements are going to be in the sample space? So how can we answer that? So what we're saying is we're choosing from the 50 tickets, we're choosing 3 of them, but the order that we write those 3 in is important. So the answer, therefore, is going to be P. We're choosing from the 50 tickets, we're choosing 3. Okay, so now we know the size of the sample space, because hopefully we can do this calculation. If you go back and check the formula, you'll see that it's n minus r on the top. So remember, this is n, this one is n, and this one is r. So it's 50 minus 3 on the top. It's factorial. And then if you remember on the bottom, I think I got it right. Actually, no, I think I got it wrong. it's equal to n factorial on the top, so it's just 50 factorial on top, and then it's what I wrote on top is actually on the bottom, 50 minus 3 factorial on the bottom. So that is, I don't have much room here, that is 50 factorial, I ran out of space, let's see, what can I do here? That is up here, 50 factorial over 47 factorial. I don't have any more space here, but that's going to be 50 times 49 times 48 times 47 factorial on the top. So just write that out and make sure you see it. 50 times 49 times 48 times 47 factorial on the top. And on the bottom we have 47 factorial. So those 47 factorial on the top and the bottom are going to cancel. So we're left with just something on the top. So that's just 50 times 49 times 48. So that's a pretty big number. But let's see if they write it down here. If they show us the answer. Yeah. So, okay, here it is. 50 factorial over 47 factorial is actually 50 times 49 times 48 because the 47 here cancels with, there's a 47 factorial in here. So you just get 50, 49, 48, which is, there are that many possibilities. So more than 117,000 different possibilities or different elements in the sample space. So that's a big sample space. For what? What is this? This is when we have 50 lottery tickets and we distribute them, 3 of them, to 3 different employees. And the calculation is choosing from the 50, choosing 3, and where the order that we write them down in is important because the order that we write them down in means the order that we give the employees the tickets who get which ticket, and that's important. If you don't think it's important, like if they're all friends and they're just going to share the winnings between the 3 of them, then it doesn't matter the order that you would write them in. Then you wouldn't really use this formula. You wouldn't say there are this many possibilities. In fact, that's the next topic. That is, when the order that you write them in is not important, then they're not called permutations. They are called combinations. Now, there are going to be fewer combinations, or there's never going to be more combinations than there are permutations. Because given any combination, you can rearrange them and get a different permutation. So there are going to be more permutations. So let's read what they say here. So they say, going back to the original question, I think, I think it was the original question where we chose 2 books to put on our bookshelf. So we had 3 books and we chose 2. So we could write that, just going back to our original question, as, so we had 3 books to choose from, and we chose 2, and the order that we put them on the shelf was important. So that would be P32 would be the number of ways, and that's going to be 6. So we count. So they said we said, for example, okay, we could have we could choose A and B as the 2 books, or we could choose A and C for the 2 books. Remember, there was 3 books. They were called A, B, and C. So we could choose A and B for the 2 books. We could choose A and C for the 2 books, or we could choose B and C for the 2 books. So first we counted the number. So these are called the number of combinations or pairs of books to be chosen. Then we counted the number of ways to arrange the two chosen books on the shelf. So there were three what we call combinations, and then we can rearrange those in two ways. So we got 3 times 2 was 6. So then we counted the number of ways to arrange the two chosen books on the shelf. Sometimes the ordering or arrangement of the objects is not important, but only the objects that are chosen. In this case, so if you don't care about the way that they're arranged on the shelf, you just care which books are on the shelf, then you wouldn't say that AB is different than BA. You don't care how you put them on the shelf. You just want to know how many ways can you choose 3 books and put them on the shelf, not what order you can put them in. So then you wouldn't count 6. You wouldn't say there are 6 different ways to select 2 books from the 3. If you don't care about the order that you put them there, you would just say, well, I could choose books A and B, or books A and C, or books B and C. So you wouldn't say the answer was 6 anymore. You would say the answer is 3. So what they say here is, sometimes the ordering or arrangement of the objects is not important, but only the objects that are chosen. In this case, we call that the number of combinations, not the number of permutations, and we can use a rule for that one as well. So if you didn't care about how many, the books, which books and the order that they're placed in, if you didn't care about the order they were placed in, then you'd need a different rule for counting how many ways can you select 3 books from 2. So it wouldn't be the P formula. So we're going to call it the number of combinations, and you would write it like this. And we already know the answer is there's just AB, AC, and AC, and BC. We already know the answer is 3, but what's the formula for this? So thinking about that question, we have 3 books, A, B, and C, and we're going to choose 2, and we're going to put them on the shelf. Now, if we care that the order is important, well, let's say we could choose A and B, we can choose A and C, or we can choose B and C. Now, if we don't care what order we put them in, then there's just 3 ways to do this. But if we care about, so we'd say there are 3 combinations. But if we care about the order that we're doing this in, then we would say, well, we could change the order of these 2. We could change the order of these 2. We could change the order of these 2. So you can see that there are going to be more combinations than there are there are going to be more permutations than there are going to be combinations. In this case, there's only 3 combinations, but there are 6 permutations. And in general, given any combination like this combination, if you care about permutations, you're going to be able to permute these. So there's going to be more, for every combination, there's going to be maybe 2 permutations, or maybe even more. We don't know. So there's generally going to be more permutations than there are combinations. Okay, so what was the formula for permutations? It was P, N, R. Now I wrote it wrong last time at first, but now I remember that it's N factorial over N minus R factorial. That was the formula before. Now we just said that there should be more of these than this. So that means this should be bigger than this. Well, is it? Is this bigger than this? Well, look at it. Stare at it. This is N factorial, N minus R factorial. Here's the same N factorial, N minus R factorial. But then we have something else in the denominator that makes this smaller. So at least in that regard, these 2 make sense. Now, why should it be R factorial? We haven't said. But at least we can see that there are going to be more here this is going to be bigger. This is bigger than this. The only time that this wouldn't be bigger than this is if r is equal to 1. So if we're only choosing one item, then it doesn't turn out to be bigger. But otherwise, it's going to be bigger. And it's never going to, this is never going to be, this is never going to be bigger than this. Okay. So the formula, they look pretty similar, except that this one has an extra r factorial in its denominator. And this says that. It says that this one was smaller, but it was very closely related to this one. It's just that this one had an extra, this one was the bigger one, divided by r factorial, has an extra r factorial in it to give us this. So we can write it like that. Okay, here's an example of where we want to use the combination, not the permutation. So when you face a counting problem, you have to decide before you use a formula. You have to say, well, do we care that is this a question where the order is important or not? If the order is important, you want to use the permutation rule, and rather than the combination rule. Okay, actually, this is not just that question, but also it's actually a probability question. So we're going to use our formulas to figure out what n of A is, and also we're also going to use our formulas to figure out what n of S is, and then we'll be able to, in this question, figure out some probability of whatever they're asking us about, which I'll call it as A. So the probability of something. So, but to figure out the probability of something, we're going to have to be able to count how many elements are in that event and how many elements are in the sample space. We'll probably need some of those formulas that we just developed to do this counting. Okay, so let's first read the problem. So it says that there are 5 manufacturers, and they produce an electronic device. And the quality is different at each manufacturer. So, there's going to be the best quality at one of them, and the second best at another one, and the third best at another one, and so on. Okay, so if you select 3 of the manufacturers, so you just select 3, like this one, this one, this one, what's the chance that the selection would contain exactly 2 of the best 3? So when I wrote 1, 2, 3, 4, I was talking about the quality, where 1 is the best quality, 2 is the second best quality, and so on. So here I've chosen 3, and does it contain, so does my selection contain exactly 2 of the best 3? So the best 3 are obviously the first, second, and third, and my selection was this one, and this one, so my selection does not contain 2 of the best 3. Now I might have instead chosen, so suppose I had the first, second, third, fourth, and fifth ones like that. So this means that this is where the first one, the best manufacturing occurred, and this is where the second manufacturing, and I'm going to select 3 of them. So suppose I select this one, and this one. So how about now? If you were to select 3, so I selected 3 at random, what is the chance that you would contain exactly 2 of the best 3? Well, actually, I my selection contains 3 of the best 3, not exactly 2 of the best 3. So even now, I didn't get what we're seeking. This is not part of the event that we're seeking. So here again, I have the best manufacturer, the second best, the third best, and so on. So if I chose like here, here, and this one, now I chose 3, and my selection contains exactly 2 of the 3 best, because 1 and 2 are part of the 3 best. So in this case, I would have selected exactly 2 of the top 3. So this would be part of the event. So, okay, with that introduction, we first want to identify what the sample space is. So in this experiment, we're choosing 3 from 5, and we're labeling the 5 not by their names, like, you know, one is in Tokyo and another is in Osaka, and not by that, but by how good they are in terms of which is better, the order which is best. So anyway, we've labeled our manufacturers like that. That's a very convenient way for this problem to label our manufacturers. Now we're selecting 3 from the 5. And do we care about, so we're probably going to be interested in either this or this. So we didn't spend too much time on this C, but we spent enough, I think. So what's the difference between these in terms of what they mean? So this is when you select 3 from 5, but you care about the order that you write them in. So here I selected 1, 2, and 5. I selected 3 from the 5. And do I care whether I write it like this, or whether I write my selection like this? No, I don't care, right? I'm just, these really mean the same thing. I got what I was looking for. I selected 2 of the best, exactly 2 of the best of the top 3 from the 5. It's a lot of words. So it doesn't matter the order that I write the selection in. So I'm not interested in the permutations, I'm interested in the combinations. So this will give me the size of the sample space. So I could do 1, 2, 5. What else? 1, 3, 5. I could do 1, 2, 4. I could do, these are the ones that are in the event, but I could do any 3 actually. I could do 1, 3, 5. I could do 1, 4, 5. These are all possibilities. When I choose from the 5, I choose 3. So this is the size of the sample space. So that's what this is. This is the bottom here is C, 5, 3. Okay, now we want to know how big is A. So we need to choose from the top 3, we need to choose 2. So once we choose 2 from the top 3, then we have to think about how many ways we can choose the other one. All right, so this is, I didn't say that very clearly, but what we want to do is figure out how many ways we can choose 2 from the top 3. So I'll write that here. So that's how many ways can we choose 2 from the top. because what we're going to want to do is we're going to want to have, like, suppose we choose 2 and 3. Those are from the top 3. And then we have to choose one more not in the top 3. So that means we have to choose one more from these 2. So that's like maybe we'll choose 5. So that's one way that this could happen. Another way is we could choose 1 and 2 from the top 3. And then we have to choose 1 from over here. So maybe we choose 5 again here. That's another way that the event A could happen. That's another way that we could choose exactly 2 of the best 3. So we have to decide how we're going to choose 2 of the best 3, and then what the other one is going to be as well. What the other one is going to have to come from here. So how many ways can we choose 2 from the top 3? Well, that can be written as C, 3, 2. 2 from the top 3. And then we ask how many ways can we choose 1 from here. And that can be written as C, 2. There's 2 in here, 4 and 5. And we want to choose 1. And then finally we use the MN rule, which says if we can do this part in this many ways, and we can do this part in this many ways, then we can do the whole thing in this times this number of ways. So this is going to be, the product of these two is going to be up for this thing, for n of a. And so that's going to be here. And so the answer is going to be this thing on the top divided by this thing on the bottom. Okay, let's see what they say. The experiment consists of randomly selecting 3 manufacturers from a group of 5. Okay, we said that. We're going to choose 3 from 5. And so that's going to give us the sample space. 3 of which are, but we want the probability of that 3 of which are designated as the best, and 2 of which are designated as not best. So I actually labeled them as 1, 2, 3, 4, 5, but they labeled them as best. There are 3 in here that are best and 2 that are not best. So maybe this is another way, a better way to express this, but let's see what they say. The event of interest is A, call it A. Select exactly 2 of the best 3 manufacturers. So this word exactly, remember, is important because that means we only want 2 from the best, and then we have to choose 1 from the not best. So you can think of a bowl containing the names of the manufacturers from which you select 3 as shown in the figure. Well, they don't actually show the names of the manufacturers. They actually label them as best and not best, it looks like to me. Okay, let's keep going. So we need n of a and n. So n is just like we said, C, choosing from the 5, choosing 3. And that turns out to be 10 if we do the calculations, which we didn't do. So now we need to do n of a. And notice that a will occur only when you select 2 of the best 3 and 1 of the not best. So they're calling that a 2-step process. And so we're going to need the MN rule because it's a 2-step process. So how many ways, so there are 3 ways, how many ways to select 2 of the best 3? That's C, from the best 3, choose 2. And then how many ways to select 1 of the 2 not best? So from the 2 not best, we need to choose one, and then we need to apply the MN rule. And so it's going to be, when you do the calculations, you get 3, and here you get 2. So it's going to be 3 times 2. It's going to be 6 as the numerator. That was n of a, and the denominator, we did the calculation, was 10. So it's going to be 6 over 10. So finally the answer is 6/10. Okay, so that is the end of this discussion, and I hope that with this, and then if you also read the book after going through this video, that the video will give you the basic understanding, then you can read the book and clarify everything, and then you should be able to do these problems. So good luck.